Hello and welcome to Chem eMind. Today we will be looking at chemical reaction engineering or simply reaction engineering. As the name suggests, reaction engineering deals with the design and operation of chemical reactors. The purpose of this video, however, is to give a brief overview of this course. Understanding chemical reaction engineering is in the understanding of rate laws and kinetics, reactor designs, mole balance and how it relates to the various reactors, stoichiometry and conversion. Chemical reaction engineering is key and important to chemical engineers as it is applicable in all aspects of reactor design, scale-up and production, process intensification, automation and process control, not forgetting the safety of the plant and environmental impacts. The rate of a reaction. Rate of a reaction tells us how much most of a chemical species is being consumed or disappearing per unit time, per unit volume. Simply, we can say that the rate of a reaction is the rate of disappearance of reactants or the rate of formation of products. Disappearance used in this context is not simply disappearance, but then the loss of identity of a chemical species. For a heterogeneous system or for heterogeneous system, the rate of reaction can not only be defined per unit volume, but can also be defined per unit weight or per unit surface area. Below are some relations between the rate of reaction and these variables. It is important to know that the minus sign used here is not negating the equation, but simply representing the loss of identity of chemical species. In industries, reactions occur in reactors due to the longevity and bulkiness of the reactions. Reactors are mainly classified into two, ideal and non-ideal reactors. The most common ideal reactors are the batch reactor, the continuous stirred tank reactor, plug flow reactor, and packed bed reactor. Packed bed and plug flow reactors, however, can be grouped as two. The batch reactor. The batch reactor is used for smaller productions as it takes in content in batches. It does not operate under a steady state, meaning that the process variables such as temperature and pressure, density and volume can be changed at any point in time during the reaction. Contents in this reactor are well mixed, though there is no flow in or flow out. Continuous stirred tank reactor. The continuous stirred tank reactor, CSTR, is also known as the back mix reactor. It operates on a steady basis and can also function as a loop reactor. The contents in this reactor are perfectly mixed, and this is a great advantage. Tubular reactors. Tubular reactors are continuous flow vessels that operate in a steady state. They are mostly used for gas phase and liquid phase reactions due to their structure or nature. Because of their pipe-like shapes, it is difficult to mix or control reactions. The general mole balance equation. The general mole balance equation is used to determine the amount of substance, mole, in a reactor while reactions are ongoing. The general mole balance equation therefore combines the flow in and flow out of the reactor with the amount of substance generated within the reactor or within the system. It is used to give the amount of substance accumulated in the reactor. Let's look at how this mole balance equation relates to the various reactors. Batch reactor. For the batch reactor, we know that there is no flow in or flow out. As a result, Fj and Fo will be equal to 0. And this will lead to this relation. T is equal to negative integral of the Na all over minus RAV with lower limit Nj0 and upper limit Nj. The equation is resolved to this because for a chemical engineer, we are interested in the time it takes a batch reactor to finish a reaction. Continuous stirred tank reactor. The NJDT or the NJDT of a continuous stirred tank reactor is always equal to 0 as it operates in a steady state, and so there is no change in mole or concentration per time. And so the equation for the continuous stirred tank reactor will be equated to 0. Chemical engineers are interested in the volume of reactants or the volume of the contents of a continuous stirred tank reactor. And so we get this equation. Tubular reactors. Or again, for tubular reactors, the NJDT is also 0 as they also operate under a steady state. Conversion and design equation. The purpose of conversion is to simply write the mole balance equation in terms of concentration. To do this, we use the limiting reagent. Conversion describes the ratio of how much reactant has been consumed. For the batch reactor, conversion is done to result in the design equation T is equal to Na0 integral of the Xa over minus RAV with lower limit 0 and upper limit Xa. Na0 here is simplifying or representing the moles in the beginning, and Xa is the mole fraction of the reactants. Minus Ra is basically the rate of reaction, and V is the volume. The design equation for CSTR. After going through this process, the design equation can be written in terms of its volume as VA0, FA0 times XA all over minus RA. The design equation for tubular reactors. Though plug flow and packed bed reactors are both tubular reactors, their area of interest, that is variables of interest, differ from one another. However, it can be seen that the answer is the same or the result is the same. So we can say that V is equal to FA0 integral of dxa over minus RA, lower limit A and upper limit XA is same for the packed bed reactor. However, in the packed bed reactor, it is its weight we are looking for. Case study. Chemical reaction engineering can be applied in all process engineering, including petroleum refining, pharmaceutical manufacturing, chemical manufacturing, and renewable energy. Thank you and have a nice day.